Here's an example of a position vector problem. Now, they're going to say, find the position vector v, okay? And they're going to put p1, p2 with an arrow over it, letting us know it is a vector. Now, like I said, unlike slope, where you could let either one be x1 or x2, these vector problems will set them for you. So point 1 is here, point 2 is here. So I just kind of always make a rough picture and say negative 2, 1 to 3, 4. Okay, and I want to go in that direction. So I know I'm kind of increasing here, so I better get some positive stuff for my vectors. Now, there's your formula for it. It really is just as easy as finding this arrow here. Okay, think of it just like slope. Well, they set this at 0.2, so that means this guy here is clearly the x2, and this guy here is your y2. So 3 minus 2, 4 minus 1, 5, 3. We write it in that form to show it's a vector. Okay? So if you were to find the slope between this guy, it's going 5 in the x, it's going 3 in the y. Because it's a vector, we care about this guy right here. And make sure you don't use parentheses with it. Okay? So the sideways little v things. Now, position vectors always start at the origin. Okay, that's just kind of their definition. So I know here was our point, here was our second point. We said this was 5, 3. Okay, position vectors just always reset to the origin. So if we get a vector of 5, 3, that means we got to end up over here. Okay, I know that's not where these guys start or end, but that's how the position vector between those two would go. So they always are reset to the origin. Okay, so you can notice this black line is the same thing as the blue line. It's the same magnitude. It's going in the same direction. We're just resetting it back to the origin. Now, there's a different way to write vectors. I don't care which way you do it. You can do it with the sideways v's that we talked about with x's and y's in there. You can also use i's and j's. Okay, and this may be, it's been a long time since I've done physics, but I do remember doing i's and j's in it. Okay, so we let I denote the direction along the x-axis. We let j denote along the y-axis. So any vector that we used to write as a comma b, we can write it with unit vectors. Okay, just like a unit rate is per $1 or per 1 ounce. The unit vector is, vectors of 1. So if you got a I vector here, that means it's 1 in the x, 0 in the y. If you got a j vector, 0 in the x, 1 in the y. And when we distribute this stuff, all we end up with is this. So AI plus B with the j component there. Either way you want to write these is fine. If you put this notation here, that's fine. If you want to do i's and j's, that's fine too. Okay? Here's some rules for them, which just pretty much makes sense. And again, either form is okay. So if you want to leave it in this form or this form. So what we're doing, here's a vector v. It's got an a1 and a b1. We're using the i's and j's here. It's the exact same thing as this. Both these are the same. You get a vector w, a2 and b2. These are the exact same thing. Okay? And here's a little alpha again, where it's not angles anymore. It's going to be a scalar. So 2, 3, 5, 10, whatever. If you want to add two vectors, all you got to do, add the I components, add the j components. Okay, it's really that easy. Okay. Now, I probably do this form more, but just be aware they're going to be the exact same thing. Okay, you want to subtract two vectors. Subtract the a's, subtract the b's. Okay, and you can group them with i's and j's, or you can use this. If you want to multiply by some constant, so 2v, 4v, okay, 10v, whatever, well, it's got to distribute to the I component, and it's got to distribute to the j component. Okay, if we make it twice as tall, or twice as long, you're going to have to go twice in the x and twice in the y to get there. So that little alpha gets distributed through both of them. And lastly, this guy, that's your symbol for magnitude. Okay, it's just your Pythagorean theorem, basically. A squared plus b squared, square root it. Okay, and that's why it's always, always positive, because you're doing a square root there. Okay, so let's see some examples for this. Here's a vector v, 3i plus 2j, 3, 2. Same thing. Here's a vector w, negative 4i plus 1j, negative 4, 1. Okay, they want you to find v plus w, v minus w. Okay, I'm just going to show you the answers here written in both forms. Here's where we're adding them together. So they took the I components, grouped them together here. This guy had 3i, this guy had negative 4. If we're adding them, we're literally just going to add those two numbers. So they grouped them like this, 3 minus 4 to give you negative 1i. They took the j components, 2 and a 1, they grouped them here to give us 3j. Okay, this form down here may be simpler for you guys, but do write these out. Don't try and do too much in your head here. So we're taking 3, 2, we're adding negative 4, 1. We can literally see those pieces match up, and we get here. You give me that answer or that answer. Either one of those is fine. Subtracting them now. Same idea, but we're not going to add the I components anymore. We're going to subtract them. So last time it was 3 minus 4. This time it's 3 minus 4 gets us to 7i. Okay, 2 minus 1 gets us to 1j instead of 3j. This is the other form down here as well. They're doing the exact same things, just without i's and j's. You give me this answer, you give me this answer. They're exactly the same. Okay. Here's where we do the scalar thing, and here's where we do the magnitude. So 2v plus 3w. So see if you guys can multiply 2 through this, 3 through this, and add them together, and also the magnitude. Okay, so if you want to pause that and try and scribble those down, I'll show you guys the answers here. That's what you should get. We're taking 2v. Okay, I usually do it this way. So 2v is 6, 4. 3w is negative 12, 3, and then we're just adding them together. 6 minus 12, 4 plus 3. Okay, magnitude, we're doing magnitude of v. We could also do magnitude of w. 3 squared plus 2 squared is 13. We square root it, square root of 13. Okay, one of the last little things here is this unit vector, okay, in the direction of v. So we use a u to represent a unit vector, okay? So for any non-zero vector, so it's got to have some values. This thing here is a unit vector that has the same direction of v. Okay, unit vectors always mean 1. So we're taking literally just vector v, and we're dividing it by the magnitude. Okay, and that creates a unit vector. Okay, so here's what we want to do. Find a unit vector in the same direction as v equals 3i minus 5j. So here's all we got to do. Start down here, find the magnitude of v. Okay, I'm not even including the negative 5 there, okay, because negative 5 squared will be positive 25. So literally just do this, ignore the signs. Okay, you found the magnitude of v to be square root of 34. All you got to do is take that, replace that there, copy vector v on the top. Okay? So we're going to say unit vector in this case is 3i minus 5j over the square root of 34. Now you may see it written like this. Either one of those answers is okay. I'd probably split it up. Okay, it's just how you're going to see this. Now, here's it all written out nice and formal like that. What you can see they do is this where we ended. They went and rationalized this guy. Okay, so we'll figure out how we kind of want the answers with those. Okay, we should probably rationalize, but if we go back to this guy right here, and we think about what does a unit vector mean, okay? We've done unit rates. We've looked at things like that, okay? It always means a 1. So if you find the magnitude of the unit vector, let's see what happens. So basically, I'm going to square this, and add it together. So what we just did is we found a vector with the magnitude of 1 in the same direction as our original problem. So this guy here is over 3 down 5. Okay, we just want a unit vector of 1. And that'll come in handy when we try and do different things with them. Okay, so we'll see you guys tomorrow with any questions.